It always feels good to come out to the stage when the Sinatra is playing in the background. Good morning, ladies and gentlemen, and welcome to the Big Data track. For those who did not have the chance to meet me yesterday, my name is Georgi Georgievic. I'm an innovation manager at ICT Hub and co-founder of Garage Lab Belgrade, and it will be my pleasure to be your host today. Big data is all around us, and we cannot wait to deep dive into this area with our amazing speakers. Before that, we would like to express our special gratitude to our sponsor of the day, that's TomTom. And please do remember to pose your questions through our DSC platform. We will also invite you to post your social media contact using hashtags DSC4 and DSC4 moments, especially on Instagram, where we are organizing a contest. If you want to win cool prizes, please do share all of your data moments with us. The winners will be announced tonight at the official closing ceremony. So do not miss the chance to win cool prizes. And now, with that out of the way, we can start with our very first lecture of the track. And we're starting with an advanced talk focusing on different methods of improving performance of OLAP queries requiring full table scans. Here to introduce us to this topic is Nikola Krgovic, Senior System Engineer at Twin Star Systems, a system administrator with 18 years of experience working exclusively with developers who spent his entire career managing Linux and Unix systems. He will be accompanied by his colleague Aleksandar Dragacevac, who is a team lead senior data engineer. I would remind you the audience to pose your questions through the DSC platform. Gentlemen, the floor is yours.
Hi, everybody. So that's nobody for my Simpsons joke. Okay. So, hi. I'm Nikola. This is Aleksandar. And we're here to talk about basically how to improve performance when doing very large-scale full table scan queries, basically on Postgre. The reason why we want to talk about this is basically the use cases. Before we start, I would like to apologize to everybody. We will be cutting this a little bit short because we originally planned this for a 45-minute talk, and then we were told we were going to have a 25-minute talk, so a lot of things had to be removed. Unfortunately, we didn't remove, or fortunately, to be honest, we didn't remove the introduction because we wanted to keep this clear enough for everybody listening to us to understand what we're talking about and why is this so important. I would like to start with a very small introduction regarding OLTP versus OLAP and what's the whole difference. Basically, when doing any kind of database work, you get into two types of database usage. One is a transactional database, the other is an analytical database. The main difference is that a transactional database is what runs your business. Transactions are bank transactions, transactions are actions on the website, transactions are anything that happens in near real time. Transactions happen a lot. Your average database who handles transactional data for a medium visit website will have a couple of thousand queries per second, every second, on an average. Those things can go to 5, 6, 8,000, 10,000 queries per second in peak hours of really a medium visited website. This is a lot. On the other hand, your analytics databases are the stuff where you get your business intelligence, where you get your data, where you get the information, how does your business run in the long term. The main difference between these is actually the time spent on optimizing them. When you have 3,000 queries per second, you will probably get pretty standard and a very small set of queries. Most of them will be one of the same, and those queries will be heavily optimized. Your database administrator will be spending a lot of time optimizing those queries. The developers will be spending a lot of time optimizing those queries, because if you have 3,000 queries a second average, and you have, say, 10% of those dedicated to one single type of queries, that's 3,000 queries a second, that's 30 million queries of that type per day. If you shave off half a second of that query, you are talking about major gains in performance. On the other hand, your analytics queries are almost never perfectly optimized. They are usually done ad hoc and in retrograde to the data already present in the system, and they are usually being done on demand because you get a query. I know a few businesses that actually do run data-driven, but most people actually do retrospective analytics, which you have the business owners who go on and ask questions. Hey, how have we been doing? What are the performance indicators? How is our business progressing? And what's going on with the business? So you get those questions which you need to get answered. And answering those questions is a process which happens once per question. You probably get the same query a couple of times a year, and that's it. So these things have very, very little optimizations. Also, there is a couple of people I know in the audience who work as analysts. Not all of them are, these guys are not engineers. These are the guys whose job is to understand business, not to understand database architecture. Often they don't even write the queries themselves. They use a ready tool which generates the queries. In our examples, we took a couple of queries from real-life use, which we saw generated by some analysts. I'm not going to say if those are machine-generated or human-generated, but those are very unoptimal queries because, again, this one can take half an hour to execute, but you can shave it down to 5 minutes, but it's going to happen now and then in 3 months. So those 20 minutes of shortening mean a lot less than shortening half a second in a transactional query. So what we do when we do the engineering part, when we optimize the system, is that we try the best we can to optimize the system for the analytics in the sense that we just separate it from the transactional data. The reason we do this, and the reason why we have two types of databases, is because when an analyst comes and when an analyst asks a query regarding data from the analytical database, those queries are very, very heavy. They will read almost all the data in the database, and those queries will probably never be supported by indexes, will never be supported by anything important, because basically if you're reading all the data, your indices have very little function. I have even had use cases, for example, where we would do a completely different database. For example, we would run a website on MySQL, then use something like Tungsten to replicate into a Postgre database for the analytics purpose. The important thing to keep in mind here is that in real-life cases, the database which will be queried with analytical questions will be separated from the production transactional database, so it doesn't pose any threat to the business model, to the transactional actions which have to happen fast. On the other hand, it will probably be less optimized than the one in the transaction use. If you're using Postgre, you will be doing some optimization. Some people who do database administration will set up their database in a proper manner, but that's about it. You will not have a perfectly optimized database, and that's something you will unfortunately have to work with. We try to share some data of how we did the optimization. And what we do, basically, Postgre optimization for analytical databases doesn't really go into so much details as it does in transactional databases because you don't have so many updates, you don't have so many things happening. But what's really important is that you have to size the hardware towards the data sets. I have seen so many examples where people try to run analytical databases on hardware which is orders of magnitude less capable than the data size. We are talking, for example, your analytical database will have a minimum amount of indices, basically because you will almost never have an analytical query which is covered by indices properly. Because those queries, as I said, are ad hoc. But those indices do still have to have primary keys on the database. Everybody knows what primary keys are, right? And those primary keys have to fit into the memory of the database server. That's the bare basics of having a consistent system. So what we did is we picked up some machines which had a relatively reasonable amount of processing. The second thing we did, and the second thing why we really love Postgre for analytical, is this work right here. Basically, Postgre will allow you to parallelize your query. This used to be a super fancy, expensive thing you had to license from Oracle or somewhere. Latest versions of Postgre from version 9 allow you to run parallel queries, which do tremendous acceleration when it comes to full table scan queries. I'm going to go just a little bit more into this. Basically, when you do an analytical query is usually something which will scan the entire database. That's why we use the term full table scan. A full table scan is a process in which you would read all the data looking for something. You have to read the entire database structure. This is really intensive on all aspects of the database management system. It's a really heavy process, and it really benefits from stuff like parallelization because you are processing immense amounts of data. So once we went into that problem, we thought of two possible solutions which we could use to do these things. One was to use columnar storage engines, and the other was to use the graphics CPU as an accelerator. Mind you, we are talking about very large databases, and we are talking about ways to accelerate performance on very complex models. The reason why you might consider columnar storage engines is basically because they will allow you to use compression, and because columnar storage engines don't usually support indexing. The whole point of using a columnar storage engine, I'm trying to rush this. Please, if you have any questions at the end, all questions are welcome. Again, we compressed this lecture twice. I'm sorry if I'm going too fast. Basically, we had, in order to create this, we tried to have a model which would be representative of a real use case. However, we could not have shown you a proper database which had history of use. A normal database will have 20, 30 columns in a table. Historical databases, I'm sure that somebody at least here has seen tables which have 200 columns. Those are the places when you really want columnar engines because, as I said, you don't want to have indices because having an index on a analytical database does a lot of slowdown when it comes to writing. Having a lot of indexes is always a trade-off in designing good database performance because your database gets acceleration when you get indexes that cover a certain types of queries, but gets deceleration when you have indexes every time every time the data is changed because all the indexes have to be changed as well. And having a lot of indexes can cause a lot of problems. So one of the ways which we've thought we might have a good approach towards doing this is to use columnar storage engines because columnar storage engines have a lot of good way of solving this because they store every column separately. So instead of having a proper relational databases are basically row-based. They store a single row in a flat format. Having a flat format means that you cannot use any compression of the data and that you have to use indexes. When you use a columnar storage engines, every column is stored separately from all the other columns. This means, in turn, that for when you want data only from a few columns, you only need to read that data. You cannot read data from a relational database skipping columns. Anytime you write select A, comma B, comma C from some table, the storage engine internally has to read the entire row from disk and then pick the results you want. The only case when you can skip this is if you have covering indexes. In a physical world, in a relational database, you need to read everything. The other solution which we wanted to use is something called PGStrong, which is based in CUDA and which allowed us to massively increase the parallelization of running those table scans because basically we were able to install a GPU chip in a server and to use that chip to the CUDA library to use it to process in parallel insane amounts of data. Because basically when we were running with Postgre, we were running something like 8 parallel queries. When we were running on CUDA, we were running like 400 parallel queries. So those are basically, when we originally made this design, we wanted to have a lot more test cases, but we had to shrink it down again due to time, and I'm already behind schedule. So basically, we did an initial test with pure Postgre, we did a test with columnar storage engine, then we did a test with GPU, and then we did an aggregate testing. What we didn't do, we wanted to do several of these tests with very slow disk performance. We wanted to do these tests with other cases, but again, the time limit has been the factor why we decided not to do it. So let's get to the data model a little bit in more detail. This is a basics example of what you might have in a table defining some users. This has been, we didn't take this from a single client. This is something we generated randomly for this conference, but it should cover data from several different clients, and we try to make it reasonable. What's the thing to look out here? First of all, as you can see, you have about 20 columns. This is an ideal case. This means that you have people who know what they're doing. If you were working with people who use the same database for 5 years, 10 years, this might be 200 columns. A lot of data may be duplicated, changed, and so on. So this is one of the reasons why we had certain types of results. We had a very small example, about 165 million rows. 160 million users is a good size for a user database, but it's not really a complex query pulling those users. This is about 3 gigabytes of test data, because that's what we were aiming for, something. And then, we wanted to make a test which we could test in a manner which would be repeatable. If somebody wants to have access to a test model, we can talk after the conference, we can meet, we can give you a copy. If you want to repeat the results of this testing, please contact us with any questions or anything. But again, you can just randomly generate something like this on your own. When we were starting to looking for types of queries which would best describe analytical scenarios, we went with 3 different queries in our first iteration. I only had input on the first one from my experience, which is a relatively simple query, which I've seen so many times. This is the one where you go to the marketing and they say, hey, we have a new product and we want to target a specific audience. Can you please find all our users who are certain age, certain amount of money, visit the website, yada, 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 yada. Everybody who's been doing business analytics had a lot of these queries. So what's the point? This is a targeted marketing campaign towards some people. This is not a generated query. This is the only query. The other 2 queries, which we'll discuss in a minute, are queries that have been created by people who do, by either the analysts or machine generated. I'm not going to tell you which one, because I want to respect some people. But basically, you have to understand, I like my analysts. They're good people. But those are the people who need to understand business. Those are the people who need to understand the business model. Those are the people who need to understand, sit on meetings all day, listen to the clients, listen to the customers, write those things down, and then generate data from their questions. Those things are hard. I can't do that. On the other hand, those people are not the very best when it comes to optimizing SQL queries, because basically nobody can do everything. I mean, let's be honest. So this is the only query that has been written actually by, let's say, a data engineer. The interesting part here is this could never be covered with an index, because there was just so many data, so many criteria you want. We have 165 million users in the database, and we have successfully targeted 88 people. Why is this important? You have 150 million people who you have as in your database as your website users. 88 have been targeted for a certain campaign. That's an enormous reduction. You can never contact 160 million users. You can't send emails to 160 million users. With 88 users, you can call them by the phone. That's the reason why we do all this stuff. That's the data reduction we're talking about. Sasha, you want to take the second one?
Yeah.
Also, what Nikola didn't mention, we tried to use as many types in that table, like decimal, integer, boolean, and everything to put in that first query conditional. Second query is one of common mistake. We have select in select, which will result in over 1 mil's full table scans, which is totally unoptimized, but it's a great example for our benchmark and we to see how will our samples handle this. That's a second query. And third one would be we use some mathematical calculation trying to show GPU power, and that we get most benefits, but let's say what we got.
Yeah, okay. What I would like to point out here from the engineering perspective in both queries is that you either have a select within a select or you have complex joins. I will just get into that a minute or two later because that's really important because of the results we got. Now, when we wanted to talk about the hardware results, we decided to test fully on AWS. The reason to do this is because this is a science conference above all, and we wanted to have repeatable results. This is something you can test. So basically, we just took a pretty decent instance, and we tried to get the same CPU, the same level of parallelization, with the same type of course and the same speed of course. And then we just, on one test, where we just ran them on a latest, pretty state-of-the-art, you know, not the latest, but one gen behind Intel Xeon Broadwell processor, and on the other one, we ran something with the Tesla V100 GPU, which is, I think, still the state-of-the-art you can get. So that was the whole idea, to create some tests which would be, let's say, repeatable. The first results, as you can see in baseline, are not so interesting. The single full table scan runs pretty okay. The complex select within select obviously works a lot slower, and the complex join takes minutes. When it comes to be really interesting is that in a full table scan, columnar storage actually worked slower. There were two reasons that this happened, but the main reason is that basically columnar storage engines are slower when it comes to small amounts of tables. Where we would have a benefit is if you would use columnar storage is a good use case if you have to use it in a single database which would cover both the analytical and the transactional loads, or where you would remove a lot of indices. As you have seen, our original example was a dedicated OLAP database which had no major indices, just the primary key, which removed all the constraints which are actually a good use case for the columnar storage. Now, what's missing here, what we didn't get to test, and we're already running out of time, and this is frustrating, is that we actually got in complex multi-passes, we got slower times. What we couldn't put as another 5 slides is that around here, we got around 900 up to 1,000 IOPS in peak of AWS. This went down to 600 IOPS. Mind you, this is still faster. This is pretty comparable, honestly. I mean, we're talking 5 seconds on a 15-minute score, that's nothing. We got 30% less disk IOPS. Now, that's a big thing. If you have a system which is constrained for disk, this is still a big thing. So columnar storage engines will give you a major improvement when it comes to disk yield. Next slide is really interesting. This was a big speed up. This is 10% speed up. This is also 10-15% speed up in GPU. And when we got to joins, we had an increase. The other interesting thing, and the only thing that took us so long to do this testing is we had to redo the entire test for this use case because we saturated the AWS storage and we had to reprovision storage. With GPU testing, we went up to 7,000 IOPS on a 160 gigabyte table. That's a lot of disk I/O. We really drowned the disk. Why was this? And of course, we did the combined test, which actually showed us something in between, which is something which we would expect. Now, this is a science conference, so we kind of wondered why is this happening, and we went into the data and we looked and we came to the following conclusion. When you do a full table scan on a GPU and then you want to join that data, that doesn't work. Your GPUs can do full table scans, but when they need to do a join, they need to pull that data and then move it back through the bus into the main CPU of the system, and then feed the main memory, and the main CPU is the one doing the actual join, which is definitely non-optimal, which tells us one major thing, that you should not use the GPUs are not a good tool if you have more than one full table scan. They will offer you major parallelization, but they will not offer you major benefits if you join the data. The other thing which we couldn't get is we had a driver which was able to bypass the entire bus and allow the GPU to talk directly to a PCI-based NVMe disk. We tested this on small scale in our lab, but that's not a test you can reproduce, unfortunately. You can't do that on AWS, and we can't. It's not really nice to present on a conference something that doesn't work. But basically, what happened is that you can get much better results if you put everything in the same box, but you can't do that in the cloud. So there are use cases where actually a cloud will not get you the best possible results. We wanted to test this hypothesis, so basically we tried to build a test which will do so many parallelizations and shift so many data back and forth between the CPU and the GPU to prove if our initial assumption is right. So we built another query where we wanted to find something that will work slower on a GPU. That's the really interesting part. So basically it's a pretty complex query, but with a lot of joins. And basically we managed to get about 7,000 rows as a result. Took us about 3 minutes on Postgre. We ran this thing on AWS on a GPU. Now, you have to understand, AWS is a disaggregated system. The GPU is not in the same box. We actually went through the documentation. They use GPU over Fabric. Storage is iSCSI based. So basically you have 3 different boxes who talk over a converged network which shift data all together. And other than running data on a single box, which we more or less managed to do with Postgre, the GPU took 90 minutes and then we killed the tests. I mean, this is like 40 times slower with the GPU. Why? Well, because there was one join, there is another join, and there was another complex where, and then after all that you will do a group by. So all those data had to be parallelized by a GPU, pushed to the CPU, and then let's do it all over again. And of course you can't fit all these sub-results have to fit into the memory. So basically, again, we're out of time. And let's try with the, I'm sorry again to everybody, this has been really rushed up. If you want, please talk to us after the conference. We will be here most of the day. What did we learn? Well, basically we learned one thing, that compared to a Postgre 9, which I know a lot of people are still using, Postgre 10 offers some amazing improvements. It allowed us to create easily read-only and asynchronously replicated slave, which is an amazing tool to use in analytical databases. We learned that columnar storage engines do have their place, even in places where you have a little bit of columns, but can be a tremendous asset with historical, not so well-optimized databases. And also, they're a great asset if you are low on I/O. And honestly, I have never met anybody who told me, I don't know what to do with my I/O. I have too many IOPS, I'm not using them. Everybody's using that stuff. Also, we learned that working with GPUs can be good only in certain edge cases. Unlike people who do neural networks, where GPUs are an amazing tool, because your neural network will entirely fit in a GPU memory. Your neural network model is 4-5 gigabytes. And when you have 5 gigabytes of data, you fit all that data into the GPU memory, and that thing flies through it. Once you have to push the data all over the system, you have massive speed downs, and GPUs on a database make sense in our opinion, after all these tests, only in on-prem solutions where you could have everything in a single box, and NVMe drives and GPUs in a single box, and only for running a certain types of queries, like targeted marketing campaigns. In those cases, they are still good asset, but in most cases, unfortunately, for database, accelerators don't work. And also, one thing which we really learned is that I've been telling this to people for years, latency is a big thing when it comes to disk I/O. Everybody needs predictable latency on hardware. That's probably the only use case where the cloud still may have some problems. If you need predictable latencies, that's one of the cases where you could go with on-prem. Databases are the last big place where going on-prem still makes a lot of sense. And finally, there is no silver bullet. Really, you need, when it comes to major problems, to huge problems, you need people who can optimize your queries, unfortunately, manually. No tool can do great machine-generated queries. With all due respect to a lot of vendors who are really trying to make great tools, when your data hits a certain amount of size, and this was a small table, this is 20 gigabytes, this is a minuscule table, 150 million rows is nothing. People have 150 billion rows. 150 million rows is a relatively small table, and you will still see bumps with badly written queries. So if you can get to large amounts of data, you will need people to optimize queries properly. Anything else you want to add? Yeah, we're definitely out of time. I'm terribly sorry about the time, people. We really planned for a 45-minute talk.
We have 2 more minutes for questions.
Okay.
So I think you partially answered the first one. Can we use columnar storage engine within MySQL database?
Within MySQL, yeah, sure you can. I mean, there are use cases when it makes sense. MySQL, yeah, if you want to run analytical queries in MySQL, sure. I mean, I've even seen extensions for using MySQL on Hadoop. There are different solutions. It comes down to something you would have to test and measure, but yeah, there are solutions for columnar-based engines on MySQL.
How do you overcome situations when you need to search part of text like function? And what is the best practice for this?
In my opinion, if any way possible, if you want to search in real time, get a dedicated full-text search engine like Elasticsearch or something. Those things can have a problem because of the Java heap size needed. You need to get your data set into a Java heap. That's about 60 gigs for reasonable amount of performance. But if you need it for a website in a real-time situation, I would definitely suggest that you go with something dedicated like Elasticsearch and then just hop back into the database on a primary key. And if you want to do analytical queries, then I guess you can still use it in a database, but do expect very slow performance.
And the last question from Bojan Nikolic, does this kind of acceleration opens a new exploit to SQL?
New exploit?
If Bojan could...
Look, I think it's an amazing tool, but it's a use case which is definitely shown to be an edge case. So if you have to search to insane amounts of data, and you have this is really a great tool to utilize your I/O, to utilize to gain massive acceleration if you have a proper hardware. If you want to do it on-prem, and so it is an edge case. But on edge cases, you could probably get 10. We did some more tests in a lab scenario, and on edge cases, you can get almost 10 times faster results. So yeah, it's still a very good case. That's why we did the talk. It's an amazing case, but it's an edge case. So it's not something you can use on cloud. You have to use it on prem. You have to invest, and you have to make a custom rig just for this. If you can afford it, you will still get very good results, especially if you want to build something like a data warehouse model where you would create a data mart, and then you would export data into that. And then when a business user comes and you want to give him fast results, yeah, then it's a great edge case for this.
That would be all. Thank you very much. If we can
Thank
get
you.
a huge round of applause.